Alrighty. Okay, so in section 7.3, which is kind of the halfway point of chapter 7, we make the transition from talking about exponential functions to talking about logarithmic functions, defining what they are and how they work and kind of where they come from. Logarithms are used a lot throughout math, and they have a direct tie to exponential functions. So we're going to kind of explore that as sort of an intro to logarithms. The EQ is what is a log or logarithmic function and how do they relate to exponential functions. So as a brief little warm-up, if a population of squirrels in a forest increases by 21% per year, there are currently 5,200 squirrels in that forest. How many will there be in the year 2030? Okay, so it's kind of all the necessary information. If you recall from 7.2, we wrote, or actually from 7.1, we wrote equations that look like this, times 1 plus r to the t, where a of t is just like our future amount of, in this case, squirrels. So little a is our starting value. So we're currently starting with 5,200 squirrels. We always start with 1, where we need 1 in the parentheses because that would signify no change. Multiplying by 1 would keep that population the same, but we're increasing by 21%, so I will need to add on. If you remember the tricky thing, the only thing that you really have to remember with this is that you need to change the percentage into a decimal. So I can't put 21 in the parentheses. I need to take 21% and write it as a decimal, which in this case is 0.21. So increases by 21% would be 1 plus 0.21. I put the 11th power because currently we're working in 2019. So the year 2030 would be 11 years from now, 11 years later. Okay. And then at this point, I'm ready to type in the calculator and figure out the future value. The only thing I am going to do is take 5,200 and kind of clean up the inside here. I like to write it as 1.21 because that way I know what the growth factor is. Like very specifically, if you're asked what is the growth factor in this problem, you don't want to say 0.21. You don't want to say, something. Instead of saying 1 plus 0.21, we can just shorten it and say 1.21. So from here, I'm going to go ahead and go to the calculator and type this in to get my future amount of squirrels. So 5,200 times 1.21 raised to the 11th power will give me 42,329 squirrels. Which if you think about is a huge population increase. That is, going from 5,200 to 42,300. The population gets way out of control. That wouldn't be a very realistic thing to have occur because predators, right? There are squirrels everywhere. Predators would help to bring the population down. But in this problem, if it just increases without anything holding it back, it would be over 42,000 squirrels. Okay, in section 7.2, we talked about graphing exponential functions. So we're going to take a real quick look at one of these just to get back in the swing of things. So if I want to graph this equation, y equals negative 2 times 3 to the power of x minus 2 plus 4, what we did is we first said, okay, let's not worry about these translations, just moving right or left or moving up and down. And let's first just look at negative 2 times 3 to the x. Times 3 to the x power. So I'm going to go ahead and type that into my y equals menu on the calculator. So I'm going to hit y equals, and then I'm going to type in negative 2 times 3 to the x power. And then we're going to go to the table. So hit second graph. I want the numbers from negative 2 to positive 2. So that gives me negative 0.2 repeating, negative 0.6 repeating, and then negative 2, negative 6, and negative 18. Okay. Now, what we want to remember is that all of these functions, all of these exponential parent functions, have the same horizontal asymptote. And remember, the horizontal asymptote is a line that the graph gets really close to, or it approaches, but never quite reaches or crosses that line. And for exponential functions, it's always y is equal to 0. That is our current horizontal asymptote, which is what HA stands for. And then when we have these translations, I'm now going to take those into account. So when I see this x minus 2, that tells me I'm going to shift the function to the right 2 units. And then plus 4, I'm going to move up 4 units. Moving to the right 2 is going to make me add 2 to all my x coordinates. And y coordinates are going to be increased by 4 since I have... since I'm moving up 4. So here, if I add 2 to all of these, I go from -2 to 0, and then 1, 2, 3, and 4. The y coordinates are going to be 3.7 repeating, I believe. And then we have, for -0.6, this is 3.3 repeating. And if we keep adding 4, I have 2, and then -2, and then -14. But what we need to also remember is that if you move a exponential function up and down, that also moves the horizontal asymptote with it. So that line that the graph approaches but never hits is no longer going to be at 0 for this. It's going to also move up 4. So our horizontal asymptote is going to be at y equals 4. What I'm going to do is I'm just going to go ahead and go right up to y equals 4 and draw in a dashed horizontal line. So I know that my graph should not cross that line. Not only does it help who's ever reading your graph, but it helps to remind you that, hey, like, don't go past this line, don't cross it. This should be what we're approaching. So if I then plot the points I have, 0, 3.7, 1, 3.3, what was it, 2, 2, 2, 2, 3, -2, and then 4 is negative all the way down in the basement at -14. Okay, again, I'm concerned with sort of this left half of the graph, so it's basically flat lines, and then it turns down very sharply and quickly. I'm going to throw an arrow on the other end here just to show that it keeps going, and that's a pretty decent sketch of the graph. At least gives us the idea of the shape. Again, based on what I'm looking at, that is a negative growth. Again, the growth factor is 3, so I know it's exponential growth, but we're starting at a -2, or -2 is my a value. So in that case, yeah, it's going to move things along. Okay, so the idea of a logarithmic function, or logarithms, they are defined as like the functions that are inverses to exponential. Okay, so exponential parent functions would be like y equals 3 to the x, y equals 2 to the x, y equals 1.5 to the x. Whatever number you choose here, there are some similarities. They all have a horizontal asymptote at the x-axis, which is also known as y equals 0. And they actually all go through the point 0, 1. Again, that's because a parent function has a starting value or an a value of 1. Because the parent function is defined as only being a number raised to the x power. Logarithms, as you can see the statements, there are some similarities. The logarithms are just in reverse of that, though. The parent functions for logs will always go through 1, 0 instead of 0, 1, again, because they're just inverses, so you're switching x and y. And that means that the horizontal asymptote that we have for exponents becomes a vertical asymptote. So the logarithmic graph will get closer and closer to a vertical line, but never actually cross it or touch it. That's just kind of like big picture stuff. We'll look into some specifics in a minute. The way logarithms are written is we're not going to write that full word every time or almost ever. So a lot of times you'll see logs written like this. It's the letters log to signify that you're talking about a log. And then there's this subscript number. Subscript just meaning it's lower, it's below, and smaller, kind of like an exponent is, but just again in reverse. That's called the base number. So we have log, log, and then a base number, and then we have what's called the argument. I call it the argument. I think there are some other names for it as well, but that is either a variable or a number that comes right after the base. So the way you would read that is y equals log base 10. You actually use the word base to signify that you're talking about the base number. The logarithm log base 10, our whole number system is built around base 10. So if you see on your calculator, and we'll look at this in just a second, if you see a logarithm that is missing a base, we assume it to be base 10. Okay, so a lot of times, like, right, if you see x, you can assume that that's 1 times x, or last chapter we saw if you had a square root with no index, you could assume that, or sorry, if you saw a radical with no index, you could assume it was the square root. In this case, if you see log, if you ever see log written like that, we will assume it's base 10. And if you don't write a base, then I will be assuming that you're working in base 10. So make sure that you pay attention to that if you're not supposed to be base 10. So if we look, there is actually a log button on the calculator. It's on the left side here. So we're going to try typing in log 100 just to see what that looks like. So if I hit log, then it just asks for the argument. Again, it's already assumed here that the base is 10. So I'm going to type in 100. Log of 100 is equal to 2. So I could say log 100 equals 2. You could also say log base 10, but again, you could just say log 100 equals 2. And then if I try log of 10,000, that is equal to 4, which is kind of interesting, right? You have 100 is equal to 2, and then you take a much, much larger number such as 10,000, and it increases the value only up to 4. There is a reason for this, obviously, and we're going to talk about that right now. So logarithm is, again, we said it's the inverse of an exponent, or they are defined from exponents. So for instance, if you were to type into a calculator, and we'll talk about how to do this, log base 2 of 32, you would get 5. And the reason is because this number raised to that power is equal to that. Okay, so the base number raised to the power of the answer is equal what we call the argument. Okay, so that's what, like when you're reading a logarithm, that's what you're seeing. So log base 2 of 32 equals 5 is true because 2 to the 5th is 32. Same thing here, log base 3 of 81, that is equal to 4 because 3 to the 4th gives me the number that I have inside the logarithm. So it's kind of working backwards, right? You know the base, and you're trying to figure out 3 raised to what power will give me 81 is essentially what you're doing. So it's a way to solve for exponents if you don't know what the exponent is. And then finally, log base 6 of the fraction 1 over 36 is negative 2. And this is actually pretty important. Because recall that negative exponents take numbers and move them to the bottom of a fraction. So if I had 6 to the negative 2 over 1, that would become 1 over 6 to the positive 2. And 6 squared is 36. So that's where we get those numbers from. Okay, this is key right here. This the similarity and how a logarithm is read and what you are understanding what you're reading and what you're trying to find. So just real quick, if we fill out this table just to practice switching between log form and exponential. So if you have the logarithm log base 5 of 125 equals 3, that is true because 5 to the 3rd power is equal to 125. So that's the exponential form of the same statement, just written as a logarithm. So if I have 6 to the 4th equals 1296, this is where we got to be careful. We have log we always called this the base. Like when you're dealing with exponents, the big number is called the base. And so with logarithms, it's convenient because the base number is the same thing. We just write it subscript. What's key here is that we have to put the answer next, or like the argument for the logarithm has to be what's the final answer in the exponent. So this would be log base 6 of 1296 is equal to 4. Okay, so don't put log base 6 of 4. That's a common mistake because students see 6 and 4 right next to each other and assume they stay next to each other. But here it has to be the 4 and the 1296 kind of switch spots. Okay. So log base 7 of 149th equals -2 is the same as saying 7 to the -2 power is equal to 1 over 49. Which again, negative exponents just would take that 49 and put it in the denominator. And then -5 to the -2, you could rewrite as log base -5 of 125th equals -2. Because of the way that exponents are defined in logarithms, the base of a logarithm has to be greater than 0. Must be greater than 0. Okay. So even though this is the correct way to write this is nothing that you'll ever see or have to do algebra with, because we can't have a base that's negative. So it's good to practice, but just understand that the base of logs will always be a positive number. If I wanted to do the same thing with equations, right, just like an exponential equation where, there's a variable involved and I have to solve for something, I don't want you to solve these. I just want to, again, just get practice rewriting this. So if I have 8 to the x power equals 256, I would rewrite that as log, not base 2, log base 8 of 256 is equal to my unknown value x. Okay. Again, we're not solving it. We're not typing anything in. I just practice translating from exponential into logarithmic. X to the 5th equals 298. That would be log base x of 298 is equal to 5. And 3 to the 7th equals x. I would rewrite as log base 3 of x is equal to 7. Okay, so again, just right now rewriting between the two forms, because once we need to actually start solving for variables, this will be very useful and helpful to us. So if you want to evaluate a logarithmic expression, such as log base 2 of 8, okay, understand that you are trying to find what number. I'll use a question mark. So log base 2 of 8 is equal, oh my gosh. Log base 2 of 8 is equal to what number? If I were to take this and rewrite it as an exponent, it'd be 2 to what power equals 8. So that's what you should be thinking in your head. The base number raised to what power will give me this. In this case, we know 2 to the 3rd is 8. So log base 2 of 8 is equal to 3. Okay. So we need to be able to mentally think our way through logarithmic expressions and what their values are. Again, I will show you how to use the calculator, but just want to get used to what this is saying and where these numbers are coming from. So if I have a log base 4 of 1 equals x, this is saying 4 to what power gives me 1. It's a little tricky. It's not 1 because 4 to the 1st would be 4. This is actually 0. And that was one of the first things that we reviewed from our exponent rules, is that any number raised to the 0 power is equal to 1. So I would say log base 4 of 1 is equal to 0. And again, I could test this by using the exponent function on our calculator. 4 to the 0 power is equal to 1. So that's how we're going to be evaluating these logarithmic expressions and things. So go ahead and try, if you want to rewrite it as an exponent, you can. So log base 3 of 243 would say 3 to what power equals 243. I could guess and check here. I'm pretty sure it's 5, 3 to the 5th. Yep. So I would say what we would write down here then is log base 3 of 243 is equal to 5. Log base 2 of 256, again, you're thinking 2 to what power equals 256. That works out to be 8 if you try that in the calculator. And log base 7 of 1 over 343. If you see a fraction, you should automatically think that this is going to be a negative value in all likelihood. I know 7 to the 3rd power equals 343. So in order to make it a fraction, I'm just going to make the exponent negative. So 7 to the negative 3 would be 1 over 343, which means my result here, my evaluative amount is negative 3. So log base 7 of 1 over 343 gives me negative 3 there. Moving right along. One of the things now we're going to do is graph the logarithmic function. In order to do this, I can't stress this enough, we're always going to start, and this is kind of goofy, we're going to start with the inverse. Okay, we're going to graph the logarithmic function by finding the inverse of, or starting with the inverse of it. And you might say to yourself, well, how in the heck do I find the inverse of this? Well, if you think you're right, we know that to find the inverse, I'm going to switch x, I'm going to do this down here. To find the inverse of log base 2 of x, I know I need to switch x and y around. So this would be log base 2 of y. And the cool thing is, to get y by itself, all I'm going to do is write that equation that we have, this bottom line here, as an exponent. Okay? So if I have log base 2 of y equals x, that means 2 to the power of x must equal y. Okay, and that's so powerful because we know what the graph of 2 to the x looks like. And so if we know what the graph of 2 to the x looks like, we can quickly figure out what the graph of log base 2 looks like just by switching the coordinates around. So that's not a proof, but it's a miniature, just kind of interesting where it comes from. So what I'm going to start with is y equals 2 to the x, and I'm going to just pick a couple values here. Okay, you'll notice I only have 3 numbers in the box, or 3 boxes, or 3 spots for numbers. So I'm just going to do 0, 1, and 2. If I plug in 2 to the 0 power, that is 1. 2 to the first power is 2, and 2 to the second power is 4. And we are going to write down where the horizontal asymptote is. There hasn't been any, right, for that exponential function, there's been no vertical translation, no moving it up and down. So that's how I know it's y equals 0. So then to find the graph of log base 2 of x, I'm simply going to swap the order of these things. So this will be 1, 0, 2, 1, and 4, 2. And just like how with domain and range, we switched the x and y, and just like with the table of values, we switch x and y. Now the y equals 0 will become x equals 0, which means I'll have a vertical asymptote. What that looks like on the graph is I'm going to go ahead and put a vertical line right at x equals 0, which happens to be the, happens to be the y-axis. So vertical line straight down that way. Okay. Then we're just going to graph these points. So I got 1, 0, 2, 1, and 4, 2. Okay, so between those 3 points and the fact that I can't cross that vertical asymptote, I can kind of get an idea of what this function is going to look like. It's going to be something like that. Okay, so just like how exponential functions started flat and then kind of blew up, here logarithmic functions like kind of rise up from this vertical asymptote and then start to just like slowly climb. So that is the picture of what log base 2 of x looks like. Last thing we have to do here is how do I graph a logarithmic function if it has translations? So side to side, up and down, whatever. Again, I'm going to spot the base here. It's base 3, which means this entire graph is coming from the equation y equals 3 to the x power. Okay, so just to kind of look ahead to the progression here, I'm going to start with y equals 3 to the x. I'm then going to go to its inverse, which is log base 3 of x. Okay, and then I'm going to go ahead and apply the plus 4 and the minus 5 to give me the final graph of this whole thing. So x, what is it, plus 4 and minus 5. So this is going to move, just so I can note, this is going to move left 4, this is going to move down 5. Okay, so 3 to the x power, again, I'm just going to pick a couple values. I'm just going to use 3 of them here. So 3 to the 0 is 1, 3 to the first is 3, 3 to the second, or 3 squared, is 9. I know the horizontal asymptote starts at y equals 0. So there's my table of values for y equals 3 to the x. Now we move to the inverse. So I'm going to just reverse these coordinates around, 1, 0, 3, 1, and 9, 2. That makes my vertical asymptote become x equals 0. And then we already know, like, okay, if you're going to move left 4, that means you have to subtract 4 from the x coordinates. And if you're going to move down 5, that means you have to subtract 5 from the y coordinates. What's interesting here, though, is that, again, just like how the horizontal asymptote moved with exponential functions, we need to also move, now with log functions, we need to move that vertical asymptote. And the vertical asymptote is written x equals 0. So since I am taking my x coordinates and subtracting 4, that is going to be where the new, or the final vertical asymptote is going to be at negative 4. So I'm going to go ahead and take away 4 from each of these coordinates, negative 1 and 5. I'm going to take away 5 from each of those coordinates, negative 5, negative 4, and negative 3. Okay, and then I'm going to go ahead and just graph this last table. Again, I'm going to start with the vertical asymptote at negative 4. Oh boy. Negative 4 here. Okay, and then I'm just going to graph my coordinates. Negative 3, comma, negative 5, negative 1, comma, negative 4, and 5, comma, 3. Oh, 5, comma, negative 3. Okay. I was like, well, that doesn't make sense. So again, those 3 points kind of tell me I'm going to have something that looks like this, and then just sharply turns down and does not cross that vertical asymptote. So graphing log functions, make sure you go back to the, make sure you start with the exponential function that has the same base as the log you are graphing. There's your homework. Bam, we're done. I don't know how long that was, but hopefully under 50 minutes.